cases, when you are in the wild type versus the knockout, you can look at the different durations of burst and interburst. So 3, we have 4. So which means that now you have your durations, burst AHP, you have the experiments and the simulations, and you can look at your, let's say, cumulative distribution. And then you can evaluate whatever the distance. It can be Kolmogorov-Smirnov, can be any kind of other distances. And you try to have the parameter that will minimize this on all of them together, which is not that simple, because sometimes you can think that maybe one will increase and the other will decrease. So you can, for example, take the sum of the distance. So you decrease, let's say, but you can, this is a choice. This is a choice. Once you have here, you are, in principle, found the theta represents the parameter space. So if you have 6 parameters, you play with the 6 parameter at the same time. All right, and once we have this, we have the optimal set of parameters, you can start using this not only to describe, but to make predictions, to understand. Because otherwise, if your model doesn't allow you to understand what to predict, you can go to the garbage, nobody cares. All right, so that's what we did. We had this interburst interval. This is in the knockout. This we saw already. And we filled the gap. You remember before there was a gap. There was the noise wasn't clear. All the blue was question marks. So this led us to, for wild type and knockout, 2 numbers. For example, the time of the AHP, the slow, the medium, we saw that there were some differences. The synaptic property, we assume this was the same. Facilitation resting, we had the same for both. And of course, here there was some differences here for this normalized hyperpolarization amplitude. So we found out some parameters. And so what, just to show you the examples, here are, it should be the data versus the simulation. So one is the experiments, this is the blue, and the gray one are the simulations. So you can start to argue, is it okay or not? For example, this was very hard to get here, the long, this was again the experiment versus simulation, the burst duration. It was very hard to capture this, very hard. Something was, the model could not capture. Now you can start to see the limit of what you are building, the limit of the model. This is for the burst duration, this is AHP. The AHP is good because this is how we define it. We built everything to capture this, so this was fine. So this is, wait, sorry, this is the wild type, and this is a knockout. For the knockout, it was quite good. You see, which is the model we've built. We capture everything. So this is the mu. This is probably the mean and mean and standard deviation for your data, and this is the Kolmogorov-Smirnov distance that we use to estimate. So we identify ultimately 8 parameters. You can. So with this, even if we had this difference here, we said, all right, let's accept the model as it is with its limitation. So this was typically the experimental traces, the simulated traces, And you can see that we were able to capture some of this phenomenology, right? And again, this is the distribution of the experiment versus the simulation that I re-projected here. Okay, and then we started to start to ask questions. For example, why do we have such kind of behavior? The peak, why the burst duration is peaked. So you go to the burst duration, why is that so peaked here? What's the reason? Can we understand this from the modeling point of view? Now, the idea was to explore the model itself. So, the first thing we started to look at, since we had this segmentation, we said maybe if the peak here is big, or this duration is large, then maybe this duration after it will lead to a sort of very low rebound, and it will take time to come back. So you expect some correlation in the statistics between the different periods. So that's what we started to look for first in the statistics. So the correlation between AHP duration and the amplitude. So here, in the wild type, we found some kind of correlation first between the AHP duration, let's say this, the duration versus the amplitude. This was clear for the wild type, and it was almost flat for the knockout. And then we started to look at what I started to describe to you, is, for example, do we see some kind of correlation between the previous burst duration, that is, you have this burst duration, and the interburst duration. So you look, previous burst duration, you have this burst duration, and you look at the interburst duration, you look at between two bursts. So there was some correlation for I think the blue is the knockout now.
I think the red is the knockout, what you showed on the last slide.
Yeah, okay, yeah. So the blue is the wild type. So we found some correlation. Sometimes it was going to the opposite direction between. So you see, you have basically three entities to consider. Is this connected to that one? Is that one connected to this one? And is this one connected to that one? You want to correlate. Maybe it's sufficiently far away. This one and that one will be decorrelated. If this is large and large amplitude, maybe it will go to a hyperpolarization which will be more deep, and then the AHP itself, this duration will be longer. So this is what we found here, the previous burst duration, at least for the case of the wild type, was correlated with the AHP duration. Okay, so what did we do here? Distribution of HP in quiescent phase duration from the simulation. So then what we did is we started to look at this distribution with comparing experiments with simulations to explore what's the dynamical system would do. Okay. But then this was to explore. Now we said, can we predict something? So what you can look at with the model is the variable of depression and facilitation. because you cannot access this directly using an experiment. So then the model becomes interesting. And so what we found is this distribution of the depression variable. So what we found here? We found that for the wild type, basically the system, the model, the neural network, was not that depressed, living around 1, which means the vesicles are always available. However, for the knockout, when you look at the distribution, we could see a much larger distribution of depression, which is associated to a system that is depressed. So there are much more activity in this in the knockout, where you have disrupt the glial cells connectivity. So the knockout system is more depressed at burst initiation. Burst cannot last as long as in the wild type case, because if you are depressed, it means that you have less vesicle available, so less resources to generate your burst. Okay, and then we said this. How to explore? Now you have a model. How do you explore with this model the different parameters? So, how to explore the relative contribution of this AHP after hyperpolarization, the basal membrane depolarization, the synaptic noise, or the depression in this connexin knockout bursting. So we run our system with the parameter of the wild type distribution, except for, we can now decide to just change, let's say, the time of the AHP. You can change few parameters at a time, not all of them. So this will allow us to see what is the role of the effect of changing, for example, just the time to recover of the AHP. The noise amplitude, so, and the depolarization threshold T. And that's what we did. That's what we did. And this gives us information. So let's go, let's say, to 1. We don't have to go to all of them. So influence of the AHP. So you change, you put in the wild type, you now affect this with just the AHP and not the noise that, or the other one that you found when you calibrated your model through the data. And you can see how this affects, for example, the duration of the burst and the interburst duration. So you have the wild type distribution, you have your connexin 30 deficients, and you have your data. That is, this is the data. This is the one that we did when you just do this little perturbation here, but not the other. And so you can see the effect. You can see how, compared to data, how your statistics has moved. For example, if you do the same here, so this is the data, this is the same, but if you change here and you look at the influence of the membrane depolarization, you see that your statistics is not the same. So this is a way to dissect specifically the role of each parameter on your dynamics. Okay, so this is what we proposed at that time, to use the system, the model that we generated, to explore things that you cannot easily do experimentally. If you want to say, I want to switch this time scale, it's very hard. It's very hard. So that's how a model can be used in an efficient way to predict the prediction of the depression, the state of the synapses, and the role of each parameter in the dynamics. Okay, why bursting is peak is what I explained to you. I don't want to go into this. We went into the theory of dynamical systems, look at what happened when you are in the phase space, and study what happened at each time you had a peak, a burst, we found out that it was very peak. It was the time had to be short because you are in the deterministic regime. So you explore it here. You have to study what happened basically when you are going to, by the noise, cross the parametric, so you can calculate what are the exit points here. There is some mathematics behind, which is a full class by itself to understand how you use Fokker-Planck equation. You see, the Fokker-Planck equation gives you the distribution of your point, and then you can use this to identify when you exit, for example, the distribution of the path. So what you have to do is what's called WKB approximation. Again, don't want to explain this. Is just to say that with the model, using dynamical system approach connected with partial differential equation, you can understand, you can explore why you have peak, for example, distribution. It didn't come from. It's not an event that are the statistics is by chance. No, it's not by chance. And for this, you have to get involved into this kind of modeling approach. Peak distribution of exit point is associated to concentrated burst duration distribution. So this was when you exit, because the point where you exit this different line when you go from a regime to another, because this point where you exit are very focused, very localized. That's why you have more or less, when you move to this very spiking region, more or less you are around the same generic trajectory. That's the reason. Okay. What time is it? All right. I think maybe we can do 20 more minutes, and then I stop for today. The next, this came before. So now we change a little bit of subject, but with the same idea. And this is a question we asked many years ago. How do you model breathing as a spontaneous coordination of neurons? You know, when you breathe, you have inspiration and expiration. What is important is the rhythm of inspiration. When you inhale, that's the moment where you have to activate your muscle. When you exhale, they are actually already they have been doing the job, and now you have just to relax. So a question in the field was what defines the network? Is it an oscillatory clock that tells your brain to send a signal to your muscle to inhale? So you see, are they rhythmic neuronal activity or not? The question is clear. And so our answer in a short way was no. But it took us 2 years to explain why. And then let me go through this process briefly, because you have now all the elements for this. Generate a neuronal network. So I don't remember, it's 20 by 20 or 40 by 40. You have neurons that are connected according to the distance. So we took an exponential decay profile, or Gaussian. So the further away, the less probable you are connected. So basically you are connected to your neighbors, and sometimes you have a long-range connection. Yeah, we had 400 neurons, so it's 20 by 20. Then, So there are neurons on the boundary. They are connected to just only what you see here. I think the red, but I don't remember, we will see in a second, are inhibitory neuron, and blue are excitatory neuron, and I forgot what is the meaning here of the green. So let's go slowly. So what we did here for each neuron, we used what I just described to you, this class and the previous class. Model of synaptic depression facilitation. Nothing else. However, we introduced two time scales. What are the two time scales? Well, we said that for depression, when vesicles are released, it takes time for the synapse to be recharged in vesicles. And so we introduced basically two time scale. The time scale that once you have vesicles that are depleted, it takes some time for vesicle to go and refill this vesicular compartment. That's why in cells, in synapses, which is very interesting, there are different compartments of vesicles, right? There are the ones that are the pool of recycling pool of vesicle. There is a pool of readily releasable pool. What else do we have? We have a reserve pool. So, and this can be found in electron microscopy data, where you can see some cluster here. It's less clear how they are clustered underneath, and that's why at some point we did some study with Matisse to look at trajectories, and from trajectory to explore if vesicles that are the reserve versus the recycling pool had different statistical property using their trajectory, and we found different trajectories which cannot be observed by electron microscopy. Okay, so if you have your two time scales, we run the simulation. Just noise, no pacemaker, no neurons that induce a rhythm. So who can explain to me this data? Those are the 400 neurons. This is called the raster plot. Each bar is when the voltage associated to this reaches a certain threshold. What do you see? You see that there are synchronous activity at a delay or a time period which look more or less stable, more or less the same, which is interesting because it doesn't come from any neurons or any chief orchestra that tell everybody just fire. So where it comes from? So we see that you have this spike activity, and now you can use your model to look at, associated to the spike, you can look at your variable of depression and facilitation. And here, in addition, there was another, so we have two variables for depression, so this is a facilitation. And you can see that, I will explain in a second what is Y free and Y doc. There are two variables that characterize the depression. One was almost one, and was following this kind of periodicity. Okay, so this and this was for what was this? Yeah, this is an example of when a neuron is firing. When you zoom in into here, you can see the synaptic current, which is associated with, so if you combine facilitation and depression, so you increase first, this is your synaptic property, and after you decrease. Which means what? What is the meaning of this increasing phase? Facilitation means you build up calcium, which free some neurotransmitters, which will affect the ones that are around. So it's a way to propagate the fact that you are fired, and then you go to a moment, you go to a regime where you decay, which means that during this regime, you are going to, the neuronal ensemble, lose this ability to fire. But then that was not enough. That's why we had to use another variable. During some time period, nothing happened. So the system doesn't start fresh. It takes time to refill the vesicles, and so you have a sort of refractory period that will be endogenous. So how do you model all of this? You go to classical Hodgkin-Huxley type equation. You say that you have a certain capacitance you can get from the literature. For each neuron, you look at the voltage. It is given by the current. You model the current. Yeah, I didn't put here, I think, the classical Hodgkin-Huxley, but it's connected to the voltage, the conductance. So you have to include the current of sodium, potassium, a lead current. This comes from the connectivity, which we will see in a second, and the noise. And so the synaptic current here is associated to the current that we'll obtain to know how many docked vesicles we have at time t. Those are really ready to be docked. The fact that there is a stimulation, and the number of docked vesicles should be higher than a certain minimum number. So what do you get here? So this is the facilitation. This you know because I haven't changed anything compared to the model I presented to you. You have the x and y. This is the facilitation between these 2 points. But now we have to introduce, instead of having one equation for the depression, we have two equations. So before we had only one variable here. Now we have two. And these are associated to two time scale. One is to recover, and the other is to dock. And we say that when you have free vesicles, the free vesicle can disappear. Okay, this is a term to come back when there is no activity. But when there is some activity, which is characterized by here, you have to look for the free vesicles. Each time a free vesicle is going to be consumed, you have to modulate it by the number of docked vesicles, because if you don't have any more docked vesicles, if this is 0, this term is 0, it will not affect. And for the docked vesicles, this is what happens when you have the absolute number. So this, I mean, you have to basically take this term here. When a vesicle so when you have some activity, the number of docked vesicles can disappear because they become free. So this is a term to say that a docked vesicle disappear. And this is a term to say that when you have free vesicles, how the docked vesicle increase? Yeah, it increases because you have free vesicle that comes from this reserve pool, and you complete if the number of docked here is 0. Is this correct? When the maximum, yeah, if the number of docked vesicle, if it's full, you cannot get more vesicles. So this says that if you have a certain number of slots, if all the slots are occupied, you get no more from the free vesicles, right? If they're all occupied. But if you have one free, you can have a free vesicle that comes and that will occupy this. So this is the equation that you get, and we said the current. You look at the number of docked vesicles that are ready to be released. So for example, suppose you have 4, this is 0. you look at what happened. Okay, this is a time t0 before after it spiked. We had to introduce this. This is a bit artificial, but so this is the current. So you look at what happened between t0 and t, and when you use this and you put it in here, you have the ensemble of equation that I showed to you to generate the dynamics. Okay, fine. So once you have this, again, the model for a model is not very impressive. What you need is to make sure that you can generate here some kind of prediction. So what we did at that time, we repeated an experiment. So we repeated probably some kind of degenerative diseases problem. And suppose you disconnect randomly some neurons. You disconnect them because of aging, because of a disease, whatever. You disconnect and you ask, what is the frequency at which you are going to oscillate? So at some point you say that if you disrupt everything, you should not see any more pattern of oscillations. Or you start changing your property. So what happened is this. So this is a period fraction cumulative percentage of total lesion. So you start to create lesions. So you measure the lesion by, you have, let's say, 100 neurons or a certain number of connections, and you remove them. So as the number of holes that you're creating, you ask how the periods will change, the period, let's say, between oscillation. And you see that this is a simulation versus experiment, which was quite nice to see that you could reproduce these experimental results. Again, the period of oscillations, this is what happened when you start to mess up with the synaptic property. Suppose you cut the synapses, you start to see this effect, and again we had this experimental point versus a simulation. No, wait, NBQX is for, let's see. I think NBQX is for this, no? I don't see here what's the legend is written. Number of stimulation, yeah, this is what is written here. Number of stimulation, number of stimulated neurons. Bursting, yeah, so the bursting probability, number of stimulated neurons, no, okay, so what I said is correct. This was the number, the NBQX is for this experiment, so this is this axis. Okay, so this is what we have. So they started also to change the extracellular potassium concentration and see again how this was affecting the dynamics. And again, we found some very nice correlation between the experiments and the simulation. So the number of stimulated neurons versus the bursting probability, this was, if I remember, this was the bursting probability. I think this was coming from us, and this is the experiment that they did by looking at the spontaneous burst activity. And what you learn from this is that this was quite similar. That is suggesting that the spontaneous activity that we have in the system is sufficient to generate the pattern that we have seen when you have an ensemble of neurons sufficiently connected with depression and facilitation synapses. And there's a slide, I'm not sure I have it in here, where they did experiments to measure the synaptic property, and indeed they found, our collaborators, they found that you have this depression and facilitation property. Okay, so this, yeah.
Just about the data, you had so you had experiment data showing 100% of total lesion.
No, we we didn't go to 100%.
Okay.
This is,
Okay, but almost 100%.
yeah, we went to something like 80%.
Okay. Well,
80% region. So, what I showed to you today is that the reason to build a model is to try to decipher, to understand, or to predict something. The difficulty is to find, first of all, to construct the model. Second, you want to calibrate the parameters, which is the hardest, especially when you don't have the magic toolbox of having many data. Then when you have all of this, you can ask specific questions about what's the role of different parameters on the model, try to make some prediction about the organization, or simply to understand. It was unclear before we did all of this that finally there was an hypothesis that has been disrupted because people thought before that there was pacemaker neurons, neurons that will be rhythm neuron that will push the system to oscillate at their pace. It's not the case. It's not the case. There's no pacemaker neurons because you can imagine maybe there's a pacemaker neuron at 1 hertz and this one could be at, I don't know, something like completely different. 1 every second, 1 every 2.3 seconds. And what would happen if the two are together? What do the system would do? No, it doesn't work this way. It works according to the model, according to the data that supported the model, according to some kind of distribution of connectivity, some noise, the property of synapses that we've shown, leading to some stable regime. To destabilize, you need to kill sufficiently amount of synapses to get something that destroy everything. But so we said maybe this is what could happen during degenerescence or any diseases that would affect or create disruption. Okay, so that's it for modeling of neuronal networks. And now the last chapter. So I don't know what time is it. If we do that maybe next week.
18h30.
What?
18h30.
All right. So why don't we stop here? So probably I'll give 1 or 2 last classes on how we reconstruct neuronal network and glial cells. So this will be based on what we did a couple of years ago, and maybe if I think I can also include Philip's work to show how to reconstruct neuronal network connectivity from time series. And then I will ask Thibaut to come to, and also Theo to come to discuss what we did for reconstructing the distribution of glial cells in human fetus using machine learning and spatial statistics. So we have 2 more, maybe 3 more classes, and I think that's it. So we'll end probably first or second week of February. All right? Okay. Thanks, guys.